Hi, I'm Ferdia. I'm a PhD student in the Cambridge Image Analysis Group and a member of the Cantab Capital Institute for the Mathematics of Information. Broadly speaking, my work is focused on combining ideas from the hot new field of machine learning with ideas from the more mathematically well-established field of inverse problems in imaging. An inverse problem is a problem in which we have measurements y given by some function k of a true underlying image that we want to recover, corrupted by some noise epsilon. Inverse problems pop up everywhere in imaging. A notable example is the inverse problem of magnetic resonance imaging, or MRI. An MRI machine has a large constant magnetic field and smaller varying magnetic fields that together can essentially take samples of the Fourier transform of the image we want to get out of the machine. So here we would have k given by some sampling operator applied after a Fourier transform. A naive way to reconstruct u given measurements y would be to apply the inverse of k to the measurements. This doesn't always work. The inverse might not exist, as is the case for MRI, but even if it does, it might be unstable and amplify the noise to give unusable reconstructions. The field of inverse problems has come up with a number of ways to get around these issues. One of these methods is the so-called variational regularization. Here we assume we have some quantitative knowledge about a noise and can also quantify somehow prior information about our solution u. Then we estimate our image u by solving a minimization problem like this one, where the first term incorporates what we know about the noise and the second term is the so-called regularization term, which incorporates prior information on the solution. Coming back to the example of MRI, a standard way to approach this would be to solve the following problem. Where the first term is a so-called least squares term, and the second term is a total variation term that allows our reconstruction to have sharp edges. There are still some questions left to ask, like how do we choose alpha to get the best images out? And how do we sample? That is, how do we choose S? Sampling in an MRI machine takes a lot of time, so we'd like to minimize the number of samples we take and still get a usable reconstruction. So if we had some way to quantify the badness of our reconstruction, say through some function rho, and we had some penalty on the sampling pattern not being sparse, then we could try to solve the following problem to learn a good sampling pattern and a good alpha. This is a so-called bilevel optimization problem because it's an optimization problem that is constrained by another optimization problem. If we could solve this problem, we would be learning a good sampling operator S and a good alpha. Problems of this form are very hard to solve, so one of the main things we need to consider is how to computationally approach them. It's worthwhile to note that this bilevel optimization problem is not restricted to the problem of learning a sampling pattern for MRI. Any variational regularization problem in which we are uncertain of some part of the model, we can try to learn that part of the model by solving a bilevel optimization problem like this. There are many potential applications of the ideas that I've mentioned in this video. And with the breadth of the CCIMI, I think I'm in a great position to explore some of these in more detail.